Hello everyone, welcome back. I am really mad right now because I just finished recording this whole video, went back to listen to it so I could post it on YouTube, and the sound didn't record. So, anyway, I'm back again, and I know it's recording the sound this time. Today we are going to be practicing calculating equilibrium constants and different concentrations using ice charts. Now, you do not always have to use ice charts. When you know all of the different concentrations, then you can just plug and chug. And if you know at least one species at equilibrium, just one concentration, then you're going to use an ice chart. So you're going to always make sure that you have a balanced equation. It needs to be balanced. You're going to want to be able to write the equilibrium expression, which is involving your products over your reactants raised to some number. You might have to assume something. You won't always have to, but sometimes you will. And when you are doing something like that, generally your K is going to be given to you in some form. So this entire video is basically just going to be example problems. So here's our first example, calculating K from initial and equilibrium concentrations. So you have a closed system that initially contains 1.00 times 10 to the negative third molarity hydrogen. So remember, hydrogen is diatomic, H2, and 2 times 10 to the negative third molarity iodine, also diatomic, at 448 degrees Celsius, and it's allowed to reach equilibrium. Cool. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the negative third molarity, and we're calculating Kc. So the answer's on there. If you want to give this a shot without me, then go ahead. If you'd like to follow along for an ice chart review, then stick around. So I'm going to go to the next slide, and the next slide is going to have these numbers plugged in. So you just need to make sure you know which ones are your initial values and which ones are your equilibrium values. Here it's telling us initially 1 and 2. At equilibrium, you have that. So if you go to the next slide, you'll see that all those numbers are plugged in. Now, what we need to do next is figure out what goes right here. We know in order to go from 0 to 1.87 times 10 to the negative third, you have to add 1.87 times 10 to the negative third molarity. In order to figure out what goes in these boxes, however, you really need your balanced equation. So it would be H2 plus I2, it's reversible, reacts to form HI, and to balance it, this goes here. Okay, so in order to figure these numbers out, you use a mole ratio. So if I have 1.87 times 10 to the negative third molarity HI, then for every 2 moles of HI, this is from my balanced equation, I have 1 mole of H2. So I need to take this number and divide it by 2. And that is what's going to go here. And since we have the same relationship for iodine, oh, I should probably put the lines here, there, then this number will be the same. So that's what the next slide will have. There it is. So this number, if you want to double check it, it should be equal to 1.87 times 10 to the negative third, third divided by 2. That's what both of these are. They're the same thing. Okay, so now to figure out your equilibrium concentrations, you need to do this number minus that number. So the initial minus the change, or the initial plus the change, depending. So 1 times 10 to the negative third minus 9.5 times 10 to the negative fourth. will give you, oh look, there's the numbers, that's nice. 6.5 times 10 to the negative fifth. Iodine started off with 2 times 10 to the negative third molarity, so you get a slightly different number, and we already knew our HI molarity. Now, what we're going to do in the next slide, we'll have these numbers, is we're going to plug these into our K formula. We know this is H2 plus I2 reacts to form HI. So we know in order to get the correct K, we need to take our HI concentration, square it. This came from up here. And then we will put our H2 and I2. It's always good to make sure, are these all gases or aqueous? We do not include solids and liquids. This problem does involve entirely gases and aqueous solutions or aqueous solutions. So we're fine. We don't have to cross anything off of here. So the next slide shows all of our numbers plugged into our formula. There it is. And it gives you an answer of 51. Notice how there aren't any units. Molarity squared, molarity, molarity. They all cancel each other out. So just 51. It's always nice when there aren't units. So this is the most simple version of these types of problems. Here's another example. The only additional step that's happening here is they're not outright giving you the concentration. They're telling you the number of moles in the volume. Number of moles, volume. Number of moles, volume. So you have to calculate the molarity first. So I will say, all right, if I have 4 moles of N2 in 4 liters of solution, this is 1 molarity N2. And then I have 6 moles of O2 in still 4 liters. That's 1.5 molarity O2. And then 3 moles of NO in 4 liters, 0.75 molarity NO. All right, so if you would like to go and create your own ice chart and try this problem out, this is the time to pause and try it. This is something you could do without me. If you aren't comfortable with that yet, then follow along and we will do this problem on the next slide. So the very first thing I'm going to do is write out my balanced equation across the top. So here I have nitrogen reacting with oxygen to form nitrogen monoxide. And in order to balance it, that needs a 2 there. I will write ice down the side. All right, so we know the initial concentrations. We just solved for those. This is when I was dividing by 4 liters. I got 1 molarity N2. I got 1.5 molarity O2. And it's telling us we started with these. So that means we don't have any nitrogen monoxide at the beginning. That's all we've got, nothing else. Okay, and finally we know the equilibrium concentration of NO, which is, what was that, 0.75? Okay, great. So I'm going to use a different color now. These are all my givens. I got this from the given from the balanced equation and from, sorry, not from the balanced equation. I got this from the original question. So in order to go from 0 to 0.75, I must have added 0.75. Now I know if I use a mole ratio from my balanced equation, there's one of those, for, let's see, if I have 0.75 molarity NO, for every 2 moles of NO, I will have 1 mole of nitrogen or oxygen. It's the same. They're both 1-to-1 with this. So you're going to divide 0.75 by 2 for these changes, which will come out to be 0.375. Now you have to decide on what sign you're going to assign to these, positive or negative. These are the reactants. They are being used up to create your products, so their concentrations are decreasing. So now I'm going to find my equilibrium values. 1 minus 0.375, 1.5 minus 0.375 gives me 1.125. And now that I actually have all of my equilibrium concentrations, I can solve for my equilibrium constant, which is going to be my, let's see, concentration of NO, and since it has a coefficient of 2, it'll be squared, over my N2 and my O2. Okay, great. Now I'll plug in my numbers. So 0.75 squared over 0.625, oops, that's a 5. Wow, let's try that again. 5 times 1.125. Okay, you plug this in your calculator. It looks like I only have one sig fig based off of my givens at the beginning of the problem. 4 moles, 6 moles, 4 liters. That's only one sig fig. So I'd end up with 0.8. And that's it. That's our K. All right, so now that that one is done, if you did not try this one on your own, you should definitely try this next one on your own. So I would highly recommend that you pause now. So for those of you who are still with us, we have a 1 liter flask that was filled with 2 moles of gaseous SO2 and 2 moles of gaseous NO2, and it was heated. So are they giving me my initial concentrations outright? No, not really. They're giving me the moles and the liters. So I need to take this number and divide it by that. Since it's only 1 liter, then, I mean, that's kind of nice. I know that this is the same thing as 2 molarity, and this is also going to be 2 molarity. And let's see, 1.3 moles of gaseous NO2, or gaseous NO is going to be 1.30 molarity. Okay, and I got this because I'm dividing them all by 1 liter, so the numbers stay the same. Let's see, then we're going to calculate the equilibrium constant for the reaction, and they gave us our balanced equation. We already have that. Cool. So I'm going to go make an ice chart now. So the very first thing you're going to do is write your chemical equation up at the top. So we have SO2 reacts with NO2. This is a reversible reaction. And then you have SO3 and NO. Ice down the side. I'll plug in my givens. We know the initial concentrations. We know we started with 2 of that. This is molarity. 2 here. Molarity. And it told us that it started with SO2 and NO2, and then it was heated. It started with these guys. It did not start with those. No products in the beginning of it. But then it did tell us that we had 1.3 molarity NO at the very end, at equilibrium. So knowing that, these are my givens. In order to go from 0 to 1.3, I must have, oh here, we don't need that, must have added 1.3. You need to look at your coefficients in order to figure out the other changes. 1, 1, 1, 1. When they're all 1 like that, all of your numbers will be the same. It's so nice. So I'm going to add 1.30. It's a product, so I'm adding. Here I'm moving over to my reactants. That means I am using them. They're being consumed. Now you'll do the math, the initial minus or plus the change. So here I have 0.70. I have 0.70 again. I have 1.30, and that's still 1.30. And then I will use these numbers to solve for my K value. So I need to create my generic equation, and as you probably know, I'm a big fan of partial credit, so on your tests and quizzes or whatever you're doing, always, at the very least, create this. Should be worth something. I don't have any exponents because, I mean, these are all just the number 1. It's invisible. We have a 1 on all of these. So I'll have 1.3 times 1.3 over 0.7 times 0.7. And you should end up with, let's see, there are 3 sig figs, so 3.45. And that's your K. And you're done. Okay, let's try another one. This next one is, again, one that you could do without me. Just be really careful about what you are adding and subtracting on this one. So I'd again recommend that you pause, try it out on your own, and then come back. So here they're giving us moles and liters again. Moles and liters, moles and liters. So I have to change this into molarity, but they've been nice to us and they gave us that's 1 liter. So all of these are just divided by 1. So I have 0.298 molarity PCl3, 8.70 times 10 to the negative third molarity PCl5, and I have 2 times 10 to the negative third molarity Cl2. Because they were all divided by 1, the numbers stayed the same. They gave us our equation. It looks like it's balanced. Awesome. It's ready to go. So I'm going to start creating my ice chart. So first let's write that equation up at the top. So I have PCl5 phosphorus pentachloride. Practice those naming skills. And then I have PCl3 and Cl2. I want ice down the side. Plug in my givens. They told me the initial concentration, so our flask initially contained PCl3 and PCl5, but not chlorine. So my PCl3 concentration was 0.298 molarity, and my PCl5 concentration was 8.70 times 10 to the negative third molarity. Be careful that you didn't mix these up. 3s and 5s look very similar to each other. And then it told us our equilibrium concentration of chlorine was 2 times 10 to the negative third. Okay, so I'm going to switch colors now in order to go from 0 to 2. By the way, if you've been with me now, you could try pausing and seeing if you could complete the ice chart from this point on. Okay, so anyway, I had to add that. Now I need to look at my mole ratios in order to figure out the rest. It looks like they all have a coefficient of 1, which means my numbers get to be the same all the way across. So be careful, this is where things get different. This is the split right here between reactants and products. So PCl3 is also going to be a positive addition here, 10 to the negative 3. We're adding 2 times 10 to the negative third. And here we are subtracting. Because it's a reactant, because it's being consumed. So go ahead and plug that in your calculator and you will get these numbers. There's that. Here we'll have 0.300 molarity. All right. Once I have my equilibrium concentrations, that means I can solve for my K value. I think that's what they're asking for, right? After this. It doesn't actually ever ask, but yes, we are solving for K. So write your generic equation. Oops, I forgot about my PCl3. The order doesn't matter. Okay, plug in your numbers. So my chlorine was 2 times 10 to the negative third. I didn't write this in the right order. but it's okay. And I don't have any exponents added into there because my balanced equation doesn't have any coefficients that are of any interest to me. I'll plug this in my calculator. Looks like I have 3 sig figs, so I have 0.0896, and that is your K value. Let's see. All right, so that's that one. Now we're going to go on to 2 more difficult problems where you have to use more complicated strategies. So make sure you follow along carefully on these. Here we're talking about the concentration of hydrogen ions, and we're dealing with hydrofluoric acid, which, is this a strong or a weak acid? Think to yourself. Hopefully you decided on weak. And if it's a weak acid, that means that we can have a Ka value because it can reach equilibrium. If it was a strong acid, then the hydrogens would completely dissociate from the fluorines and we would not have equilibrium values for our reactants at all. So that we wouldn't have a Ka in that case. But since it's weak, we can have a Ka. And yes, you can have a Kb. If you have a weak base, you could do the exact same process. You just have hydroxide ions. Okay, so we'll need to write our equation. Let's do that first. If I have HF, which is aqueous, it is reacting with water, which is a liquid. Or there is water in there anyway because it is aqueous. We know that's in there. And we will have hydrogen ions released. Sorry, I don't know why I put a bracket there. Hydrogen ions and fluorine. There. And these guys are aqueous. So you should have lights flashing above your head. This is a liquid. It does not get included in your Ka. Don't include it. It does not go in there. No. We don't include liquids and solids because their concentrations do not change. They don't really have concentrations. Okay, we're going to have an equilibrium expression. So our Ka will be our products over our reactants, which is just HF. Do not include H2O. Don't include it. We will have to let x equal something in this, and we're going to be solving a polynomial. We'll get there. So all we know is that our initial concentration of HF is 0.1 molar. That's it. That's the only thing they told us. So that's what we'll put. I will write out my formula. And I know my water is not in here at all. Not used. ICE. This is going to take up a little more room, so keep that in mind. So they told me that I started with 0.100 molarity hydrofluoric acid. I started with that. I did not have any of the ions yet. So that's what I've got. So your first step now is to assume that something is equal to x. I'm going to assume that H is equal to x at equilibrium. Just assume it. It's fine. Doesn't matter what you assume as long as you assume something. I would not recommend assuming x is equal to whatever you know the initial concentration of. Pick something that had a concentration of 0 at the beginning. So I know I must have added x in order to get here. I know that I have a 1-to-1 mole ratio for everything from my balanced equation. So that means I must have also added the same amount of fluorine. And here I would have subtracted x. So what you're going to write down at the bottom here is a little different than usual. You're not going to have a solid number. It'll be 0.1 minus x. So then you take your KEQ and you're going to say, okay, well, it's x times x over 1.100 minus x. And we know what this is equal to because the problem told us, oh, this isn't a KEQ. Whoopsie daisy. It's a Ka because we have a weak acid. And it is equal to 3.5 times 10 to the negative fourth. 4. Okay, so that means that I have x squared over 0.100 minus x is equal to 3.5 times 10 to the negative fourth. Okay, I'm going to rearrange this. I have x squared equals 3.5 times 10 to the negative fourth times 0.100 minus x. I'll distribute that. I'm going to distribute and I'm going to rearrange and set it equal to 0. So I have x squared equals 3, oh, I didn't rearrange it like I said I would. I'll just do it more slowly. We don't need to rearrange yet. Times times 0.100 minus 3.5 times, I'm just moving that negative symbol from that x out front, like that. Okay, I'm going to crunch these numbers and rearrange so I end up with x squared equals, where'd it go? I have this written down. Not equals. X squared plus 3.5 times 10 to the negative fourth x. Be careful that you don't confuse these x with this times symbol. Maybe use a dot instead. Minus 3.5 times 10 to the negative fifth. When I multiply those, I get negative fifth. This is equal to 0. So you should be thinking back to your quadratic equation days. Ugh. And that's what we get to do here. We know that the quadratic equation states that x equals negative b plus or minus the square root of b squared minus 4ac over 2a. I know that, let's go through them. I know that a is equal to 1 from over here. I know that b is equal to positive 3.5 times 10 to the negative 4, and that's from over here. And I know that c is equal to negative 3.5 times 10 to the negative 5. So I'm going to plug these numbers in up here, and for the sake of time I'm going to assume that you're able to plug those in. And if you did that, when you deal with this plus or minus, you're going to come up with two different numbers. You're going to have x equals 0.0057 molarity or negative 0.0061 molarity. And this is where your, I don't know, common sense has to kick in. Can we have a negative concentration? Hopefully you said no. You can't. So this must be our answer. So I believe this question was just asking for the concentration of our hydrogen ions at equilibrium, and we have figured that out. Our X, which is our concentration of hydrogen at equilibrium, is 0.0057. My pen is freaking out. Let's try that again. Equals H plus at equilibrium. So this is an example of a slightly harder problem that you might have to do. Now let's just kick it up a notch. I'm going to teach you a shortcut. People love shortcuts, so I hope you like it. Generally like shortcuts. So suppose you start out with only water vapor, so just H2O, in a rigid container, and its initial partial pressure is recorded to be 0.784 atmospheres. what are the partial pressures of each species when the system reaches equilibrium? So we have water vapor that is decomposing into hydrogen and oxygen. We know it goes both ways. And we know it started out with only water vapor. Cool. And we're dealing with pressures. So if it talks about partial pressure, don't freak out. It's the exact same problem as what we've been doing, except this time instead of molarity, everything's going to be in atmospheres. So don't change anything that you've been doing. Now, the first thing I want you to notice is that this number, your Kp, is really freaking tiny. It's really, really small. That's actually important. So let's go over to our problem and see what's going to happen. So write out your formula up at the top. It did say it's water vapor, so it's okay to include. I do want this to be balanced, so let's see, I need 2 of those and 2 of those. I, C, E. All right, and the only thing they gave me was my initial partial pressure of water. There it is. And I don't have the other two. They don't exist at the beginning. It's just water vapor at the beginning. That's what they said. So I'm going to do what I did before, where I assume something's equal to x. I like picking things that don't have a coefficient other than 1. So I'm going to say that my oxygen is going to be equal to x at equilibrium, which means I must have added an x amount of oxygen. Using mole ratios, if I added an x amount of oxygen, let's see how this works. So if I have XO2 for every 1 mole of O2, I have 2 moles of H2, or H2O. Both of them are 2. So I need to multiply this times 2, so this will be 2x, which means I'll end up with 2x. And over here, again, it's 2x, but since it's a reactant, it's minus 2x, which means I'm going to have 0.784 minus 2x. Okay, starting to look a little messy, but we'll go with it. So I'll take my K, my K, but this time it's a Kp, because I'm dealing with pressures, not concentrations, but pressures. And I need the pressure of my hydrogen squared, because of this 2 up here, times the pressure of my oxygen over the pressure of my water vapor squared, because of that 2 up there. Cool. Now I'll plug in my numbers. 2x squared x 0.784 minus 2x squared. Take a look at that, make sure you see where all the numbers come from. Now, what else? We also know our Kp. That was 2.0 times 10 to the negative 42. So when you look at this problem, if you were to multiply out all of these guys and write the polynomial, you would end up with a trinomial. You'll have x cubes and x squareds and x's, and oh, it'll be miserable. So what you need to do is look at your Kp and say, this is really small. If that's really small, I'm going to use a method where you, let's say, assume x is small. So what you do is you take a look at this where the subtraction is taking place, not the numerator where there's no subtraction, just where the subtraction is. And you say, I'll bet that this x is so tiny compared to the number it's being subtracted from that it doesn't even matter. I'll bet this x is so small that it might as well not even exist. It might as well just be 0. The smaller your k value is, the more likely it is that you can make this assumption. So let's try it. Let's try rewriting this where we made that assumption. So 2.0 times 10 to the negative 42, I don't know why 4s do that, is equal to, so you do not do this to the numerator, because if we put a 0 up there, then the problem's over, there's nothing. We only do this when we are comparing our x to a number it's being subtracted from or added to. So I got rid of it, it's gone, because I'm assuming it's so tiny compared to that 0.784 that it is insignificant. I will distribute this 2 out now. So I have 4x squared times x over 0.784 squared equals 4x cubed over 0.784 squared, still equal to this number over here. I'm going to rearrange it, so I have 4x cubed equals 2 times 10 to the negative 42 times 0.784 squared. Sorry, that's getting jumbled. I'm going to divide both sides by 4, and I'm going to take the cube root. Whoop, 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 cube root, there. You can access the cube root on your calculators through the math key on most of them. Some of them might have a shortcut. Mine is just through the math key. So you should end up with x is equal to 6.7 times 10 to the negative 15th. So we wanted to know, what was this asking for? The partial pressures of each species. So let me grab a different color here, but green. So my oxygen, sorry, not a concentration, my oxygen partial pressure is 6.7 times 10 to the negative 15 atmospheres. My hydrogen is that times 2, so that would be, what was that number? 1.3 times 10 to the negative 14. And then here it's 0.784 minus that number times 2. So this one actually comes out to 0.784 again. So this is the small x assumption method. And in order to prove that it was valid to even try that in the first place, what you need to do is take x divided by the initial concentration that you were comparing it to. So in this case, you were comparing it to 0.784. You're going to multiply that times 100. And this number needs to be smaller than or equal to 5%. So we will take 6.7 times 10 to the negative 15 divided by the number we were comparing it to, which was, hold on, it should be, sorry, hold on. We want to do 2x because that's what we were dealing with. So it's 2x over 0.784 times 100. So let me just get my calculator and see what we get. 2 times 6.7 times 10 to the negative 15 divided by 0.784 times 100. And wow, that is a small number, which is good. That's what you want. This is equal to 1.7 times 10 to the negative 12th. So basically what you can say here is, aha, I was right. X is so tiny that it is insignificant. If I had gotten like 5.5 here, that's greater than 5%, I would actually have to go back and redo the entire problem without removing my x. But since I was able to show that it is less than 5% of that initial concentration, then I'm good. Okay, we will practice more of these for sure, but this is just an introduction to the concept. So hopefully this made sense. If not, please come prepared with questions to class tomorrow. Okay, have a good rest of your day.